So, welcome all of you. We are almost coming to the end of this course with only little bit of material to be covered. In the last class and last couple of classes, I discussed about one dimensional version of several experiments. For example, 1D-TOCSY, which is a steady state experiment, steady state NOE experiment, where we can selectively saturate one of the peaks and then I do identical experiment off resonance, apply as RF power far away from the region of interest, so that any disturbance if it is there should be identical for both the experiment. The off resonance saturation, call it as a reference spectrum, and then take the difference between the one which is selectively saturated with the reference spectrum. And even if there is any NOE enhancement, if there are peaks which are NOE coupled, you will see the signal enhancement. So that is what we saw, and then we took one or two examples how NOE can be utilized, and I showed you how in simple cases we do not require to do the two dimensional experiment which is time consuming. You can do the same 1D version of NOE steady state experiment in most of the cases for small molecules. If there are isolated peaks, if we can do the selective saturation very precisely, that is what is important. Frequency selection for the saturation is very important. If there is a mistake, then what will happen? You will spill over the RF power to the neighboring peak. As a consequence, it is going to be a problem. So still I showed many examples for A and Z conformation, regiocentric identification of particular substitution in the final ring, and lot of some examples we understood by steady state NOE difference experiment. And we went into TOCSY experiment, similar one dimensional way, instead of doing a 2D, if it is a simple molecule and if you know the isolated peak, and if you can saturate selectively that one, and you can see the enhancement of the signal intensity are not enhancement, where you are going to see the signal which are connected to this, because TOCSY is a coherence transfer, magnetization transfer takes place among the coupled spins. Like in the NOE there is no J coupling, there is no need of a J coupling. Here J coupling is essential in the 1D TOCSY experiment, even 2D TOCSY experiment. We went to one dimensional version and I showed you identical you can do. I took the simple example of one molecule. I quickly, about in last 2-3 minutes, I did not go through very carefully and I simply rushed through, so that there was no time. Now we will cover take that molecule again and see one or two examples before going to a different topic. So I will start with the analysis of a simple molecule like selective TOCSY and methyl alpha glucoside in a particular solvent. As I told you, when the sugars are there already, most of the time they are all generally unbranched carbon chains. The most carbons are CHS, and we can think of them as a linear system. That is what I said. So in the case of linear system, I discussed and I said you can do selective excitation. Spin TOCSY is like a diffusion process. What happens? I start with, let us say, this one. I selectively radiate proton A. Then what will happen? Start with selective excitation of A, it gives magnetization to B, depending upon the strength of the coupling and the duration of the mixing time. That is very important. It will give magnetization to that. I keep on increasing the mixing time. Then slowly it gives the magnetization to C, A will give to C, C will give, and then to D, and then to E. Of course, it goes through A, B, C, D. It is a sequential process. It is propagation of the magnetization in the TOCSY I told you, it goes among all the coupled spins. But it is not unidirectional, although I have shown it as unidirectional here. It is always the magnetization transfer goes forward and backward. A will give to B and then B also will give to A. All those things we discussed as such when we discussed about TOCSY, especially 2D TOCSY. With this, what happens if I selectively exit not the proton which is at the end of the chain, somewhere in the middle? And it can so happen if I start with a selective excitation of, let us say, proton C, then the magnetization is given to B and D, because they are next to each other and they are coupled to each other. Depending upon the coupling strength, they will be identified. Magnetization transfer takes place for B and D, and then next give the mixing time larger, then it will go to A and E also. Like this, you can start with a particular proton, selectively saturate one of them, selectively, and then selectively excite, and then transfer the magnetization to all the coupled spins of the spin system. So we can do that, and I showed you this in this example, how selective excitation is going to be done. If I take for example one of the protons here, this proton, if I selectively excite and enhance the signal intensity, you will see there is some enhancement here. And mixing time is very important. And the mixing time is given here. This is how the selective excitation is done. And then when you transfer the magnetization, it goes to the one which are immediate coupled partners, and then depending upon the mixing time, we will go to the next one like that. It start like this in this molecule. We start with CH3, we can easily assign, that is CH3, and then all other protons we can easily assign. Most important you should know is H1. Anomeric proton generally in sugars come between 4.5 to 5, around 5.5 ppm, depending upon the alpha or beta, which type of sugar we have. So anomeric protons generally easy to detect and easy to assign. And also I told you, depending upon alpha and beta, the coupling strengths are different. I told you already earlier, axial coupling is larger than axial equatorial, and equatorial is much smaller than both of them. That is what we discussed. So depending upon the coupling strength, you can even identify alpha and beta isomers. So we start with this. I am selectively, let us say, saturating proton 1. Then what is going to happen? You see, it is saturating OCH3 which is next to each other. This is proton 1. It is saturating OCH3 next to each other. And then partly it also gives energy to other proton which is coupled to it. This is this one. So that could be H3. It gives you H2, H1, OCH3 and also to H2 and also to H3. All the three it is. See, for example, you see for H3, the magnetization transfer is much less because it is not immediate coupled partner, it goes 2-3 bonds away. So you require more mixing time. First thing you should understand, I have saturated proton 1 and I see this enhancement of OCH3 and proton 2. They are very close to each other. And then they are coupled, the strong coupling is there, and you are seeing the magnetization transfer. If you carefully see, if you enhance the signal intensity by about 12 times, you will see the polarization transfer to other proton. What is other proton? Obviously, if you go by the chain, it must be proton H3. So like this we can continue. Okay. And then what we will do is, we will enhance the mixing time. Remember in the previous example, previous slide I showed you, H3 was less in intensity for 30 milliseconds mixing time. The same H1 is selectively saturated or excited, and then the magnetization transfer is done. As you see, for proton 3, H2, everything is there. At the same time, now because of the mixing time being larger, magnetization transfer even gone up to H3, proton 3. Alright, this is what it is. And then if you see carefully, it is going to other proton also, not only H3, further, that is H4. What is happening here? Nothing. We just simply enhance the mixing time from 30 millisecond to 50 millisecond, but we saturated the same H1 anomeric proton. First it goes to OCH3, which was very close, but then among the J coupled partners of the spin system, it gives to H2 and then to H3, and slowly also it is going to H4. So like this we can make the assignment easily. We will start with, let us say, now I know H1 and immediate coupled partner we saw where the magnetization transfer is H2. To understand further, what we will do is we will selectively irradiate H2. Wherever this wavy arrow is there, that means that is the place where we are selectively exciting. I selectively excited proton H2, but you see, as we observed in the previous example, H3 is getting saturated. Of course, when H2 is radiated, there is also small contribution to H1 because H1 and H2 are coupled, and you see H4 is also getting excited. You can see that magnetization is transferred to H4 also to some extent. Okay, after H2, what we will do is we will go to H3. We are irradiating proton H3 here. Then what we expect? H3 is far away, small exit, transfer here, negligible, but then major transfer is for H2 and then to H4, because H3 is H2 and H4 are immediate coupled partners for that. So the magnetization transfer is taking place more for H2 and for H4. Alright, to go further, to confirm systematically we can go one after the other, then we start irradiating proton H4. When you irradiate a proton H4, of course, you can slowly see it is here when you irradiate H3, small magnetization transfer to H5 also. When I do H4, what do we expect? Immediate coupled particle is H3, there is enhancement is more, and then it further gives magnetization to H5. What next? It will go to H6 also. I'm sorry, H2 is also there, H2. So, this is what is happening, and you can see small magnetization transfer to H6 here. We are irradiating H3. It is something, you know, systematically you can go from H3, H4, and then you come to H5, irradiate H5. You will see there is a magnetization transfer to H4, H3, and also here little bit magnetization transfer to other proton. What is the next one? Is the coupled chain system, coupled spin system. It is H6 obviously. H6, and H6 are two protons, A and B I have identified. So, one is A, and you can see partly for the other one also there is a magnetization transfer. To continue to understand this better, what we can do is we can selectively saturate proton H5. You can see H3, H6 and H4. To confirm more, we did one of them which is isolated, which is H6. Obviously, H6 will give magnetization to other H6A because they are having a geminal relationship. It gives magnetization to this. So, H6 was selectively irradiated. You can see magnetization transfer to other proton of that. On the other hand, if you do selectively saturate this proton, you will also see this. But here when you irradiate this proton, there is a magnetization transfer to H5 also. That shows we can say this is very close to H5. All right. So, we can understand this thing, and complete assignment can be done by selective TOCSY. Selectively I can excite one of the protons and allow the spin system to mix up, and then thereby we can transfer the magnetization among the coupled spins. Okay, we will go to another simple example, which is the glucose. It is 2D glucose, 2D-dimensional 2D COSY. We have already analyzed that one, and then we have also understood D-glucose exists as two conformers, alpha and beta, with alpha with 64% and 36% here. Okay, we can see we can almost make the assignment for alpha and D beta. We always start with anomeric protons. Anomeric protons I told you which comes downfield around 4.5 to 5.5, and of the two, each of the anomeric protons will only be a doublet because it can couple to only one of the single proton, which is proton 2. If you consider anomeric proton is H1, it can only couple to another single proton, which is H2. As a consequence, it is a doublet. Of the two doublets, you can identify which is beta and which is alpha, because I tell you assignment of alpha and beta is so easy. Beta has a large coupling, about 8 Hertz coupling, because it is axial coupling. Alpha has only 3.8 Hertz coupling, which is only axial equatorial coupling. As a consequence, assignment of anomeric protons can be straight away done just by looking at the doublet separation. So, doublet separation of 8 Hertz, I can say it is beta, and the other one is alpha. All right. Another one important thing is we have OHS and everything get exchanged with T2O. Fine. But when you look at the spectrum and also intensity of the alpha and beta anomers, the ratio is 64:36 for both the peaks. That is true, because we also know that 63:36 is the available ratio, which is close to the literature value. So, 64% and 36% are the two enantiomers which are supposed to exist in water. That is known. So, if you get the intensity ratio 63:36, by and large we are close to the literature value. And if you say, if you identify a peak of intensity 63 relative intensity compared to other one, then we can assign that as a single proton pertaining to beta isomers. That is what we do. So, there are, if we consider two isomers, anomeric proton, of course that I already said, which is all half field and low field, just now we discussed, there is no need to go for that. We will see this one now. This is beta, this is alpha. Okay, this is alpha. Fine. What next? If you see that all OHs are exchanged, the peaks with an integral area of 0.36 correspond to 1 proton of alpha. I told you, peak, if you measure the integral area, a peak of 0.36 intensity if it is there, it corresponds to alpha anomer. If there is a peak with 0.63 intensity, it corresponds to beta anomer. If there is intensity 1, what does it mean? It is an overlap of alpha and beta anomers together. So, if there is intensity 1, we can identify and say one proton from alpha and one from beta are overlapped. As a consequence, the intensity becomes 1. So, integral intensities are given here. What we can see is, we will start all the blue things which I have put highlighted here, all the peaks which intensity 0.36. They are all one proton from alpha. Okay? And those which are written in green are intensity 0.63, you can see here, 0.64, close to that one. That means they are all from single proton of beta anomer. But of course, you can also see some of the peaks with one intensity here. This is one alpha peak from alpha anomer, one from beta overlapped, give rise to intensity 1. But here there is an interesting thing, we have 1.39 intensity. What does it tell you? It tells you 2 peaks from alpha and 1 peak from beta are overlapped here. So, by integral intensity, area of the integral, let's say of the peaks, we can start making some assignments. We do not say which proton is which, at least we can say which are the protons coming from alpha and beta, how many are overlapped. That information we can say. Here one peak from one alpha and beta overlapped, here 2 from alpha and 1 from beta is overlapped. All right. And of course, we can also find out from the J coupling and everything, identify the peaks very easily. Okay, here it says 2 peaks from alpha anomer is overlapped and 1 peak. Finally, all the assignments we can obtain like this. Now, to identify more, what we will do is we will do the selective TOCSY. We all know, from the previous this thing I showed you, we can identify which are the peaks from alpha, which are the peaks from beta by integral intensities and where are the overlaps. Fine. We will have specifically assign all the protons based on TOCSY. Of course, we can do 2D-TOCSY to identify, but if you do not want to waste much time, 1D-TOCSY is much easier. As I always start with the anomeric proton, which is downfield. I know this is proton H1. I saturate selectively that one, give certain mixing time, select after exciting that. Now give mixing time, but there is a polarization transfer takes place. One, as you know, should give magnetization to 2, which is immediately coupled to. And then depending upon the mixing time, it can give magnetization to 3 or 4 like that. With 30 millisecond mixing time, it is giving magnetization to 2 and partly little bit to 3, very weak intensity. To confirm more, the same experiment can be done with enhanced intensity. Of course, we can also confirm that by doing selective irradiation of proton 2 instead of 1. If you do proton irradiation of 2, what will happen? It gives magnetization to 1, to 3. And then also little bit for H4, you can see little bit for H4. And to ensure you are okay, our experiment is in the right direction, you can give more mixing time, make it 50 millisecond. You can see the intensity enhancement, you can clearly see. One which was very weak, very clearly you can see. All right, what we can do is, we will now selectively irradiate. We have already irradiated, selectively irradiated this one H2 and then H2 with a higher mixing time also we saw. We selectively irradiate proton H3. Then where do you expect the magnetization transfer? H4 and H2. H3 is in between these two. And then depending upon the mixing time, we can also see part of magnetization transfer to H5. So that can be H5. And of course, H6 also is there. And H5 is DDD and is also coupled to H4 and H6 and HA. See, that is another interesting thing. See, what is happening is if you are irradiating this one, you are going to get the magnetization here. But if you irradiate H3, H3 is giving magnetization to H4, H2 and also to H5. To some extent it also gives to H6, one of the H6 protons. That is what is happening here. So, what we can do is to confirm further, we can selectively saturate one of them. Okay, now we will do this one, selectively saturate one of the thing which could be, I will say, proton 6, because H5 we have identified, H3, H4, H2 everything we have identified one after the other, and the last one left over is H6A. That was we saturate this one or excite this one, and you will see magnetization transferred to H6 because they are geminal relationship. Okay, we can make the assignment. Go further. That was our alpha isomer. We can start with other one, that was for beta. Okay, now start with the alpha isomer. Again, where do you start? You start with the anomeric proton. Irradiate that. If the anomeric proton is always 1, it has to give magnetization to 2. Where is this strong signal intensity? Here. Then this has to be H2. And also slowly you can see some magnetization is given to that one. That must be H3. Okay, so to confirm that, irradiate H2, H3 becomes more, and then H1 is also getting some signal. But also when you are irradiating H2, some magnetization is given to other proton. Obviously, as I said, it is a unbranched chain sugar ring, it has to be H4. That is done. And if you enhance the mixing time, the intensity becomes very clear. Alright, we can now saturate other protons. For example, this one, what else it should be? It has to be H6, one of the H6. When you irradiate that, we can see it is giving magnetization to its geminal partner H6A and also to H3 and also to H4. All are getting magnetization transferred. So, this way what I suggest is a selective saturation, selectively excite the proton, allow them to mix up, you can transfer the magnetization to its immediate coupled partner, enhance the mixing time, it can go to the next one like that. Alternately, if you know irradiate one proton, go to the next one, you will see the enhancement there, go to the next one and irradiate that, it gives magnetization to the previous one and also the next one, then go to the next one, like that systematically you can go one step after step by step, and then selectively excite each proton and then allow the spin system to transfer the magnetization among the coupled spins depending upon the coupling strength and depending upon the mixing time given, you know which are the coupled protons, because you will see the enhancement of the signal intensity in those protons where the magnetization transfer has taken place. This way you can make the assignment of all the protons in a simple way by doing one-dimensional TOCSY experiment. You don't need to do 2D-TOCSY and then of course spend a lot of time. This is okay if you are to do only 1 or 2 experiments. If you have a very big molecule with hundreds of peaks and closely spaced, overlapped, then this type of 1D selective TOCSY is very difficult, because your frequency selection for excitation is not precise then. So, it will be very problematic. In such cases, as usual, you can do 2D transient NOE experiment. So, this is what I am telling you, 1D type of experiments for faster data acquisition, very simple molecules, where you can see that there are isolated peaks and you have a degree, when you have a difficulty in identifying which is the proton, then this type of experiment can be done. So, I have covered 1D version of NOCY, 1D version of TOCSY. Of course, this is not the end. Yeah, 1D version of HSQC, 1D version of TOCSY, 1D version of ROSY, 1D version of COSY. All experiment can be done in a one-dimensional way. All this can be applied, but I am not showing everything because already we have discussed this. Only 2 examples I wanted to show you for one-dimensional version of TOCSY and one-dimensional of NOSY, where you can utilize selectively for doing this thing. Same thing can be done for ROSY, same thing can be done for HSQC. Selectively you can transfer, excite a proton or so, or transfer the magnetization to its coupled carbon and then take it back and identify the coupled partners. All these experiments can be one dimension also. You have to take a judicious decision where to apply this technique. What is the type size of your molecule, what information you want to derive, so that there is no overlap, no mixing, no spillover of the RF by selectively irradiating one peak and then you should not spill out to the neighboring peak. All those care if you do, and if you are a simple molecule, I suggest you can do simple one dimensional experiment and get same information as you can get in 2D. But it is a saving of the instrument time here, that is important thing. You can save a lot of time. Okay, with this I think there is no point in going further. What I am going to do is I will go to another topic, slightly a different topic, and then we will cover that today and see what more we can do later. See, I am going to tell something about what is called pure shift NMR. What is a pure shift NMR? We will discuss something different now. What is a pure shift NMR? Before going to pure shift, two important things we should discuss in NMR. NMR is, as I told you right from the beginning, first class, there is sensitivity, the biggest issue. Okay, sensitivity we discussed at stretch about the sensitivity issue. What we did, I told you when we were talking about the polarization transfer, one of the ways go to high magnetic field, take more amount of the samples, and all those things we discussed. Alternately, what I suggested also was we can do polarization transfer experiments to enhance the sensitivity. So, there are some ways we can address the issues of sensitivity of detection in the NMR. But there is another issue, very key factor for NMR is a resolution. Of course, resolution, one of the important factor for resolution is you have to go to higher and higher magnetic field experimentally. And it depends upon certain physical parameters in the experiment. For example, if the molecule is aggregated and it is not, there is no mobility and it is a viscous solvent like that, you have broadening and everything, resolution issues are there. That is one thing. But remember, resolution, the definition of the resolution in NMR is half the sum of the line widths should be greater than the separation. For example, I have two peaks here. This is well resolved, I would say, because I take line width of this one, line width of this one, I will take half of the line width of this, half of the line width of this. Take the sum of these two, half the line width of this peak, half the line width of this peak. That should be greater than this one. Half the sum of the line width should be greater than the separation, in which case we can say these peaks are well resolved. That is the resolution. But resolution also is not only because of this, there could be because of severe overlap. That is one thing. And another thing for the resolution, severe overlap, is also because one particular proton can experience coupling among several other protons or other heteronuclei with abundant spins. It can complicate the spectrum a lot. Because of severity, the overlap, resolution could be a problem. So, there are the two, sensitivity and resolution are the two factors that are key factors in NMR. How do you do the resolution? As I told you, resort to very high field, you get the gain in the intensity by B naught to the power of 3 by 2, B naught is the static magnetic field. We discussed this long back in one of the classes. How do you enhance the sensitivity of low abundant spins? Broadband heteronuclear decoupling, break the coupling of all the dilute spins like carbon, nitrogen with other abundant field like proton or fluorine. You can do isotopic labeling and enrich the carbon or nitrogen 15 by doing isotopic labeling, and also do the polarization transfer by doing NMR methodology, which we also discussed. All these things can be done. So, when I say decoupling is one way to enhance the resolution. As I told you, if you are interested only in knowing the identifying the chemical shifts of the particular carbon or the proton or any heteronuclei. Broadband heteronuclear decoupling is very, very useful, especially when you consider heteronuclei like carbon. We have seen many examples when I was discussing carbon 13 NMR. When there is a enormous overlap because of each carbon coupled to different number of protons, it can give us to quadret, triplet, doublet, and singlet. When there is a severe overlap, I showed you we can do broadband decoupling. There are several types of broadband decoupling we discussed, and then when you do the decoupling, you break the coupling with all protons and carbons, and you get single peak for each chemically inequivalent carbon. That is very easy. Broadband decoupling, especially for heteronuclear, is very easy to do. And when you do that, you see what a simplified spectrum you are going to get. This is a quadret of CA3, the triplet all become singlet. Look at this one. If there is a severe overlap, it will be difficult for you to identify quadret, triplet, etc. On the other hand, when you do the broadband decoupling, you identify all the singlets like this. Next question is, how do you do the decoupling? How do you achieve decoupling? You can achieve this by manipulating the passive spins. What is passive spin? What are passive spins? When I am observing carbon 13, protons are passive spins. Okay? So I can manipulate the passive spins without touching the active spins. I will not perturb the active spins. I only manipulate the passive spins. When I do that, I can do heteronuclear decoupling in such a way I can apply the radio frequency power on the heteronuclear to suppress all the heteronuclear couplings at a time. This we discussed in carbon 13 NMR. The easiest way to do is apply a radio frequency in a hypothetical example of carbon coupled to a proton. You saturate the radio proton at proton frequency, apply a radio frequency, saturate all the populations of the proton, and then you are going to apply another RF at the carbon 13 frequency to detect the signal. The irradiation power should cover the whole range of proton frequencies, in which case you break all the protons coupled to all the carbons at a time. This is called heteronuclear broadband decoupling. This is a very easy experiment, it can be done. How it works? We discussed long back. If you irradiate let us say set of protons, they get saturated and they undergo rapid transition among all the possible spin states. I discussed this when we discussed decoupling in carbon 13. These rapid transitions break all the spin interaction between protons and the carbon 13 that is being detected. As a consequence, all heteronuclear couplings are averaged to 0, and carbon senses only the average spin state for the attached protons rather than 2 or more distinct spin states. This is a crude way of discussion, but one can mathematically work out and discuss at stage. But imagine this is what is going to happen, and we can do broadband decoupling. Especially this is the notation also I said. Okay, how much should be the decoupling power? It depends upon the strength of the coupling, and usually decoupler is set at the center of the proton spectrum, and the decoupling power should be larger than at least should be larger than the largest coupling strength, more than at least twice the larger than that. That is what we do. And what about this 13C scalar coupling? At natural abundance they are not usually visible and not intense at all, very weak intensity and difficult to detect. So with that, heteronuclear decoupling is easy, I tell you, not difficult. Now the question comes is, what about the complexity of the 1H NMR spectra? This is where broadband decoupling becomes very important, and it is a topic by itself called PURESHIFT NMR, which since the time is getting up, we will discuss this in the next class. Right now I am going to stop here. So today we discussed a lot about one-dimensional TOCSY experiment, which we had started from the last week. We showed some examples, and then I took another example today of the beta and alpha and beta anomers of glucose which are present. I showed you selectively exciting anomeric proton. We see the magnetization transfer to proton 2, and then with the mixing time enhanced it will go to a little bit to proton 3, and then saturated proton 3 it will give to proton 1 and proton 3. Saturated or excite proton 3 it will give to proton 2, proton 4 also. Like that systematically you can go selectively excite one of the protons and see the saturation and transfer the magnetization to other proton. This is what is done in a one-dimensional way. Through this we could identify, we could separately assign by doing this 1D-TOCSY experiment all the peaks pertaining to alpha isomer of glucose and all the peaks pertaining to beta isomer of glucose. I did not, we even could tabulate all the chemical shifts. All those things are not much important, but the concept, the methodology is important. That is what we discussed. Then we of course went into the pure shift NMR. In the pure shift I have not introduced about the pure shift for homonuclear spin, but heteronuclear thing is pure shift means you break the coupling, you get only chemical shifts. That is what we saw in the carbon 13 other heteronuclei. You break the coupling of heteronuclei with abundant spin like protons, and when you do that you are going to get a single peak for each of them. How you do that? You selectively saturate the protons sitting at the center, applying a radio frequency power RF power should be sufficiently larger than the coupling strength. Then you will get single peak for each of them. It enhances the resolution. Okay. Sensitive issue can be addressed in NMR, and resolution by doing one such experiment is by not only going to high field, but also doing decoupling to simplify the complexity. Okay, I am going to stop here. We will continue with the other remaining things in the subsequent classes. Thank you very much.